From an architectural perspective, a private home is a mirror, reflecting the aesthetic preferences and lifestyles of the society, the community, and the era in which that home was built. We can tell at a glance that this sprawling house, with its clapboard siding, large windows, and rural setting, was a 19th century farmhouse. That this ornate mansion epitomizes Victorian-era architectural exuberance. That this tidy little bungalow reflects the post-Victorian return to simplicity that characterized the American arts and crafts movement of the early 1900s. That this simple brick ranch home is a product of the post-World War II building boom, and that this McMansion, and a few hundred more just like it, were built in an upscale suburban development in the 1980s. Given the diversity of individual tastes and never-ending changes in architectural fashion, it's hardly surprising that residential construction comes in such a seemingly limitless variety of shapes and sizes. Yet if we could peer beneath the architectural skin of these homes, we'd find a surprising degree of consistency in structure. Indeed, every one of the houses we just looked at uses essentially the same structural system, a configuration called light wood frame construction. Furthermore, the light wood frame is one of only 3 principal types of residential structural systems that have been used throughout recorded history and across much of the civilized world. The other 2, bearing wall construction and heavy timber frame construction, are traditional forms that have been around for millennia. Light wood frame construction wasn't invented until the mid-19th century, but it has dominated residential construction in North America since then. Understanding these 3 residential structural systems is the principal goal of today's lecture. But before we can achieve this goal, we first need to discuss a few key engineering concepts that will facilitate your understanding. First, what is a structural system? Well, it's an assembly of structural elements that work together as an integrated whole to carry such diverse loads as the weight of snow on your roof, a tub full of water in your bathroom, the china cabinet in your dining room, a crowd of people attending your cocktail party, a gale force wind, and the weight of the house itself. Okay, so what's a load? Well, quite simply, a load is a force, that's a push or a pull that's applied to a structure. Now, this concept is simple, but the process of determining the magnitudes, directions, and configurations of loads for the purpose of structural design can be quite complex. Fortunately, this process is greatly facilitated by building codes, those important regulatory documents I introduced in the last lecture. The International Residential Code identifies 5 principal categories of load that are most relevant to our understanding of residential construction. The first is called dead load, the weight of the building itself, including structural elements like beams and columns, non-structural components like shingles and windows, and permanent fixtures like bathtubs and kitchen cabinets. Dead loads are fixed in both position and magnitude. They're usually associated with known quantities of physical stuff, so their magnitudes can be determined quite accurately without a lot of detailed guidance from the code. This brick, for example, weighs 3.5 pounds. And on that basis, we can estimate the weight of a full brick wall with a very high degree of confidence. But the second category, live load, is a very different story. Live load consists of the weight of people and all of their movable stuff, like furniture, books, and housewares. Live loads are highly variable in both magnitude and position, and they can change dramatically over time. Given this inherent unpredictability, we need to rely heavily on the institutionalized wisdom of the building code to help us estimate these loads. For example, according to the International Residential Code, my living room floor should be designed to support a live load of 40 pounds per square foot applied to the entire floor surface. Note that live load is specified as a pressure measured in pounds per square foot. But what does this number really mean? Well, to attach some physical significance to the code-specified live load of 40 pounds per square foot, I've marked off this carpet with a series of 1 foot by 1 foot square tiles. And now I'd like to ask 6 volunteers from the Great Courses staff to join me here in the studio and to stand as close as possible on this grid without actually touching each other. Now, prior to this lecture, I asked each of our volunteers how much they weigh. And the total of all 6 weights works out to 1,020 pounds. Yes, this is half a ton of people. As you can see, our volunteers are occupying approximately 12 of the squares on my floor grid, 4 along the front, 3 along the side. And so the live load represented by this very tight grouping of people is 1,020 pounds divided by 12 square feet equals 85 pounds per square foot. But wait, that's over twice the code-specified loading that's been used to design living room floors in nearly every house in the United States. How can this possibly be? Well, the answer is that for design purposes, the code-specified loading is assumed to be applied over the entire floor, not just one small segment of it. So a true 85 pound per square foot live load applied to my living room floor would require enough people to fill my entire living room from wall to wall, all packed as tightly together as this group of 6. That would actually be about 200 people. But this simply couldn't happen, in part because a substantial portion of my living room floor space is already occupied by furniture, but also because there's simply no circumstance under which 200 people would be in my living room. Thus, even though a live load of 85 pounds per square foot is physically possible, it's so unlikely to occur in a residential space that the code allows us to design for a much lower loading. Now, by the way, people do stand this close together quite often in the corridors of lobbies, public buildings, and theaters and auditoriums. And not surprisingly, the code-specified loading for public corridors and lobbies is not 40 pounds per square foot, but 100 pounds per square foot, which actually gives us a nice margin of safety beyond the 85 pound per square foot loading we just derived from this simple experiment. Thank you, live load. Now, a moment ago, I mentioned that a large portion of my living room floor space is taken up by furniture. How is furniture taken into account in the code-specified live load of 40 pounds per square foot? Well, just for fun, let's do some more math. Here's my living room couch. The piece itself weighs 350 pounds, and it seats 3. If we assume conservatively that these 3 occupants weigh 200 pounds each, then the total weight of the couch plus people is 950 pounds. This piece of furniture covers a floor area 3.5 feet by 7 feet, or 24.5 square feet. And so the loading associated with this rather heavily loaded chair is 950 pounds divided by 24.5 square feet equals 39 pounds per square foot. And so for this more realistic utilization of living room floor space, the code-specified loading, 40 pounds per square foot, is quite reasonable. Now, through this discussion of live load, I hope you've gained some deeper insight into the practical value of building codes. In the absence of the code, determining an appropriate live load to represent a specific planned usage of residential space would have required extensive research and considerable engineering judgment. But the code made this task easy, providing us with a single number, 40 pounds per square foot, that was formulated by experts and validated through its use in the design of many thousands of structures. Our third category is snow load. Like live load, it's specified in pounds per square foot, but unlike live load, snow load is applied to the roof of the structure, and its magnitude varies according to the building's geographic location and roof configuration. Code-specified snow load varies from 0 in Florida to over 100 pounds per square foot in northern Maine. That's an astonishing amount of snow. At 100 pounds per square foot, a modest-sized home with a 1,500 square foot roof surface would be designed to support 150,000 pounds of snow. That's 75 tons. But The required design loading can be reduced significantly by using a more steeply sloped roof with a smooth, heated surface, like this metal roof, such that accumulating snow will slide off before it gets too deep. The code provides all the necessary adjustment factors to account for these variations. Now, by the way, dead, live, and snow loads are often grouped together as gravity loads, so named because they're all associated with the weight of something, building materials, people, furniture, snow, and thus are always oriented vertically downward. Our remaining two categories of loading, wind and seismic, are fundamentally different in that they're not associated with gravity and are applied primarily in the horizontal direction. For this reason, wind and seismic are often called lateral loads. Wind load is caused by moving air striking and then moving over and around a building. Let's see how this works. This simple model represents the walls and roof of a building. And this fan, out here on the other end of my device, will simulate the wind blowing across that building. In between is a very crude wind tunnel, which will help straighten out the airflow coming from the fan. So, what's going to happen when I turn on the fan? Well, as you've probably predicted, the moving air will exert pressure on the upwind wall of the building, pushing the wall inward and causing the building to lean a bit in the downwind direction. In hurricane-prone regions, this pressure could be upwards of 40 pounds per square foot. But what you might not predict is that the moving air will also cause suction on the roof and the downwind wall. These elements will actually be pulled outward. The roof will be pulled upward, the downwind wall outward, in response to that suction. The effect is quite subtle, so watch very carefully. Now, to understand what we just saw, and therefore to understand how wind affects a residential building, we first need to discuss two key concepts from fluid mechanics, a branch of physics dealing with liquids and gases, both of which are classified as fluids. First, whenever a fluid flows through a constricted region, the velocity of that fluid increases. You actually observe this phenomenon every time you take a shower, as slow-moving water in a pipe is transformed into a series of fast-moving jets emerging from the tiny holes in your shower head. Second, when the velocity of a fluid increases, its pressure decreases. This is called Bernoulli's principle, named for Daniel Bernoulli, who discovered it back in the 18th century. As we apply these principles to wind load, the fluid is air, and the constricted space is the region above the building. As the wind flows through this region, its velocity increases and thus its pressure decreases. Consequently, the air pressure above and behind the building is lower than the pressure inside the building. And this pressure difference forces the roof and the downwind wall outward. The two net effects of these pressure loadings are a substantial horizontal force and a net uplift force, both of which can significantly influence the structural design, as we shall see. By the way, the wind-induced uplift force on a building is entirely analogous to the lifting force generated by air flowing over an airplane wing. And in both cases, the Bernoulli effect is the underlying cause. Of course, there is an important difference. Uplift is highly desirable for an airplane, but it can be quite problematic for a building. Indeed, wind-induced uplift is a particularly important concern in residential construction because these lightweight buildings can actually be lifted completely off their foundations in extreme windstorms, particularly when they aren't properly bolted down, as was apparently the case here. Finally, let's look at seismic load. An earthquake affects a structure by causing the ground beneath it to accelerate horizontally, like this. This motion causes the structure to oscillate rapidly back and forth, as you've seen, And with each oscillation, the lateral acceleration of the building's mass is mathematically equivalent to a large horizontal force pushing the structure sideways. We know this because of Newton's second law. Force equals mass times acceleration. As we've seen so often on the evening news, seismic effects on buildings can be devastating. And not surprisingly, seismic structural design is quite complex. Fortunately, we don't need to address it any further detail in this course, because for residential construction in all but the most earthquake-prone regions, the structural elements that resist horizontal wind force are the same ones that resist equivalent horizontal seismic force. Well, now that we've looked at the 5 categories of loading, dead, live, snow, wind, and seismic, we can examine how structures respond to these loads. When external loads are applied to a structural system, they cause internal forces, which are transmitted through the individual elements comprised by that system. A structural element will respond to these internal forces in any of 4 different ways, depending on the configuration of the element within the structural system. First, if the element is stretched, like this, it elongates and is said to be in tension. Note that the vertical black lines are getting farther apart as I pull on it. If the element is squashed, like this, it shortens and is said to be in compression. Now note that the black lines are getting closer together. If the element is loaded transversely, like this, it bends. And if you look closely, you can see that bending is really just a combination of tension and compression. If the beam bends as it does here with its concave side facing up, the black lines get closer together on top and farther apart at the bottom. Thus, the top of the beam must be in compression and the bottom in tension. And then finally, if the ends of an element are rotated in opposite directions like this, the element twists and is said to be experiencing torsion. Now, a structural element with a particular set of dimensions made of a particular material has a well-defined strength with respect to each of these 4 behaviors. For example, tensile strength is defined as the maximum tension force that an element can carry before it ruptures. It took me about 5 pounds of pull to break this element in tension, and so we say that this element has a tensile strength of 5 pounds. Tensile strength, compressive strength, bending strength, and torsional strength can be determined experimentally through laboratory testing, but more usefully, they can be predicted with fairly high degree of accuracy using a variety of different scientific and computational tools. These analysis tools are absolutely fundamental to the structural design process. Now let's put it all together. The principal objective of structural design is to ensure that, for all relevant types of loading, the predicted strength of each element in the structural system is adequate to carry the associated internal forces safely. With these concepts as background, we can now return to our 3 types of residential structural systems: bearing wall, heavy timber frame, and light wood frame. Primitive forms of bearing wall construction can be traced back to distant antiquity. Indeed, one of the world's earliest known cities, Çatalhöyük, located in modern-day Turkey, was composed entirely of domestic buildings with mud brick bearing walls surmounted by timber roofs. In the U.S., bearing wall buildings dominated residential construction throughout the colonial era and well into the 19th century. In a bearing wall structural system, the principal vertical load-carrying elements are the building's exterior walls, which are typically made of solid stone, as in this 19th century farmhouse, solid brick, as in these colonial-era townhouses, mud brick or adobe, as in this pueblo in the American Southwest, or solid wood, as in this log cabin. And here's how the system works. These are 2 of the 4 exterior walls. They're supported on a stone or concrete foundation down here. It's called a wall footing because it extends along the full length of the load-bearing wall. We'll put these in place. Now, usually, interior floors and roofs are supported on beams that are called joists that are set into notches in these exterior walls like this. Now, when a gravity load is applied to our structural system, the joists carry the load in bending. They transmit that load out to the outer perimeter walls, and the perimeter walls then transmit the load vertically downward in compression through the wall footings and into the soil below. As you can see, this is a fairly effective system for carrying gravity loads. But what about horizontal wind load? What happens when we get a large lateral load applied by a wind striking the face of the building? Well, as you can see here, the arrangement really isn't particularly stable. So the bearing wall system needs some sort of additional augmentation in order to be able to carry those lateral loads. But we can add that augmentation quite simply by adding the other two walls of the building. So I'm going to bring these back up to the correct orientation. Let's take one wall here, plug it in to this end of our sidewalls. Do the same thing on the opposite side. Once again, I'm going to replace those joists set into notches in the two side walls. And now we can add that same gravity load. But at this point now, I can add substantial lateral load, not just in this direction, but in the perpendicular directions as well. And this structural system is now capable of resisting wind loads and gravity loads of significant magnitude. So clearly the rigid walls of a bearing wall structure provide inherent lateral stability. The traditional bearing wall structural system is relatively more expensive than the other two types because those solid exterior walls generally require a lot of material, skilled labor, and time to construct. On the other hand, these buildings gain a certain efficiency from the exterior wall's ability to serve simultaneously as both structure and enclosure. And the resulting structure is both strong and fire resistant, characteristics that explain why so many centuries-old bearing wall buildings have survived and remain in beautiful condition today. Next is the heavy timber frame, a structure in which stout wooden columns, beams, and braces form a discrete structural skeleton. Like bearing wall construction, the timber frame has its roots in distant antiquity. The earliest Greek temples were timber frame structures. And in more recent centuries, this system has been used in the traditional half-timbered houses of Europe, where the wooden skeleton is actually visible on the building's exterior, and in the classic American barn, where the skeleton is covered with wooden siding. So let's see how a heavy timber frame works. I'll start by completing this partially built heavy timber frame consisting of 4 columns and 4 beams. Note that in order to put the structure together, I'm going to be using a traditional timber connection called the mortise and tenon joint. To make that joint, we have these tongues that have been carved into the ends of the beam, and those tongues are inserted into the corresponding rectangular hole in the columns, which is called the mortise. So here, a tin is inserted into a mortise at either end of the frame that I'm adding to the structure. We plug them into place, and then we secure them in position by driving a wooden peg through a hole that connects the mortise and the tenon rigidly together. Now I'm going to take my wooden frame and place it on a set of column footings, which constitute the foundation for this kind of a structural system. And when I do so, you might notice that the structure is kind of wobbly. It doesn't really stand up straight. So presumably when I put a heavy load on it, it's going to have some lateral instability problems. How can we make this structural system more laterally stable? Well, the answer to that question is best attained by calling upon the expertise of the rural barn builders who've been constructing strong, stable timber frames like this for centuries. Note in this image that in a typical timber frame, every beam-to-column connection is reinforced with one or more diagonal braces. So let's try adding similar braces to my model and see what happens. Now this is going to take some time, so please bear with me. Done. Thanks for your patience. Wow. Notice now that the structure is significantly more rigid. I can now add a floor system to the assembled three-dimensional frame. I can put an actual set of floor planking on top of that floor system. We can now apply substantial gravity load and lateral loads simultaneously, and none of the previous instability that we saw in this frame is present, despite the fact that we have substantial amount of loading on the structure. This demonstration dramatically illustrates the inherent rigidity of the triangle as a structural form. We'll see this concept again when we talk about trusses next lecture. Now, as a structural system, this timber frame is similar to the bearing wall system we looked at earlier in that gravity loads are carried by the floor beams in flexure, then transmitted out to the building's outer perimeter. But here, unlike the bearing wall system, the load is concentrated into the four corners of the floor system where it's transmitted to the columns. The columns then transmitted in compression downward into the foundation, and in this case, the foundation consists of four column footings in place of the wall footings that we saw in the earlier structure. Well, this is the second time I've mentioned footings, so we should take a moment to look more closely at what they are and how they work. Both the wall footings we saw earlier and these column footings have exactly the same purpose: to spread out the weight of the structure as it's transmitted down into the soil below. Now, note, let me remove the structure, get it out of the way, and note that on the top of these column footings, the entire weight of that structure and all of the load that's applied to it bears on these four very small squares located on the tops of the footings. But down below, the same weight bears on substantially larger areas corresponding to the bottom surface of the footings. As a result, the footings spread the weight of the building out over an area roughly 20 times larger than would be the case if the columns were placed directly onto the soil. This prevents the soil from failing or settling excessively. In effect, a footing works just like a snowshoe, which allows you to walk on soft snow by spreading your weight out over a much larger surface area. And just as feet without snowshoes sink deeply into a snowbank, watch what happens when I place this structure onto the soil with its columns bearing directly on the soil rather than transmitting load through footings. As you can see, the columns sink deeply into the soil. Even as we speak, the footings below your home are preventing this from happening. Now, the heavy timber frame is a very versatile structural system, and it's generally less expensive to build than a traditional bearing wall building, particularly in regions where plentiful supplies of timber are available. But the all-wood construction of this timber frame is also less permanent, and those mortise and tenon joints require highly skilled craftsmen to fabricate. Like this stone farmhouse and its adjacent wooden barn, bearing wall and timber frame structural systems have coexisted side by side, each with its own advantages and disadvantages for many centuries. But the economic calculus of construction changed radically in the early 19th century. At that time, the advent of standardized mill-sawn lumber and machine-made iron nails stimulated the development of a fundamentally new structural configuration that rapidly superseded both the bearing wall and the heavy timber frame systems. This new system, invented by a Chicagoan named George Washington Snow in the 1830s, was based entirely on the use of standard, lightweight, mill-sawn lumber held together with nails. Back then, critics derisively labeled it the balloon frame because it seemed so unsubstantial and fragile. But Snow's light wood frame construction method proved to be surprisingly strong, while also providing better versatility and ease of construction at a much lower cost than either of its predecessors. It caught on quickly, and with only minor modifications is still in use today as the dominant method of residential construction in the US and Canada. The modern adaptation of Snow's balloon frame is called the platform frame, and we'll be devoting all of next lecture to it. For now, we should recognize that the dominance of the platform frame in modern residential construction does not render the other two structural systems irrelevant or obsolete. Both bearing wall construction and heavy timber framing have retained a significant presence in residential construction and, indeed, have actually been staging a bit of a comeback in recent years. For example, heavy timber framing is becoming increasingly popular for high-style homes like this one, because its aesthetic qualities evoke a certain rustic charm. A recently developed bearing wall technology called the structural insulated panel is becoming increasingly popular for highly energy-efficient buildings, as we'll learn in our later lectures on energy efficiency. If we look beyond our borders, we'll see that lightwood framing never really caught on in Europe, probably because timber is not as plentiful there. Thus, modern European residential construction is still largely of the bearing wall type, using brick, concrete block, or ceramic block walls. And if we look beyond residential construction, we'll see that the structural concept embodied in the heavy timber frame is present in most modern commercial buildings. Indeed, if we could peel back the outer facade walls of the Great Course's own office building, you would see a system of beams, columns, and diagonal braces that's functionally identical to a 19th century barn frame, except that these members are made of steel rather than wood. These exceptions notwithstanding, it's quite likely that you or someone you know lives in a platform-framed house. Next lecture, we'll see how this structural system is built, how it works, and why it has dominated American residential construction since the 19th century.